In the previous lecture, which was an introduction, we have seen some of the devices, and we have seen why the semiconductor devices are important, how they help us to build better systems in electrical engineering. We also saw what are the various topics we are going to cover in this course. In today's lecture, we will discuss the uniqueness and evolution of semiconductor technology. Now, some of the material in this lecture has been taken from the chapter Origin and Personality of Microelectronics in the book titled Transistors: Fundamentals for the Integrated Circuit Engineer. This book has been authored by R.M. Warner and B.L. Grung. It's a very nice book, and if you get a chance to look at this book, you please go through it. Let us begin by trying to understand what is technology, and then we will see what is semiconductor technology. Now, technology means processing of material, energy or information so as to develop a useful product. In most general terms, this is the definition of technology. So you could either process a material or energy in some form, or even information. Okay? So that's why we have nowadays what is called information technology. Now, when does the technology become high technology? When the processing conditions are very stringent, and when the product that you get, it has very high reliability and performance and a low cost. So either you get the same performance and reliability but at a lower cost, or at the same cost you get much higher reliability and performance. Then the technology is called high technology. So semiconductor technology is a materials oriented high technology, that is, it involves processing of material, and you get products which have high reliability and much higher performance. Let me give you an example. Supposing you take the invention of the transistor, how it has changed the reliability and performance of systems. Now, before the transistor was invented, the device that was being used for amplification was a vacuum tube triode. Okay? It was made in vacuum tube. Now, the vacuum tube, the size of the vacuum tube is large. If any of you have seen a vacuum tube, you would know. Compare the size of a vacuum tube and a transistor. The size is large, then the vacuum tube is fragile because it has a glass casing. Okay? So it is said that when they built the first computer using vacuum tubes, the area occupied by the computer was something like 900 square feet, and they had a number of engineers to maintain this whole system because it would fail very often. Okay? And another important problem was how to dissipate the heat generated. So whereas you compare a computer that we use today, right, a notebook computer, or nowadays you even have palm top computers, see the power dissipated, right, see the size and see the speed. So you are getting much higher performance and reliability, right? The computers are very reliable. So this is what the semiconductor technology has done. It has given you products which are very highly reliable and which have much better performance. Now, so it is important for us to know that this advantage is achieved only because the material is processed under very stringent conditions. That is the price you are paying. So that let us understand that in little more detail. So what are the processing conditions in semiconductor technology? So what is shown here is a clean room where semiconductors are processed. So you see, you can't make devices in open air. You can't make semiconductor devices in open air. Okay? So first stringent condition is that you need a single crystal material. You make, most of the semiconductor devices are made in single crystal material. This is a very stringent condition because a single crystal material means the arrangement of atoms should be very, very regular throughout the size of the crystal. So a lot of energy and cost you are expending in getting a single crystal material, single crystal growth of single crystal material. Okay, so that is the first stringent condition. The next stringent condition is an ultra clean environment. So that is what is seen in this diagram here. So you see the person who is processing has is wearing a mask and some kind of a attire, right, which prevents any dirt from him getting into the environment. Okay, so this is not only for protecting him, the person, against chemicals and so on, but is for protecting the environment, right, against pollution by the person. Okay, so you must understand this, that this, when the size of the transistor is very, very small, of the order of microns or even submicron, it means that even a very small dust particle, right, can kill a few transistors on the chip. Okay, now how do you measure the cleanliness of environment? So people talk about the class of the environment. For example, a class 10 clean room, what does it mean? It means that there are no more than 10 particles of size more than fractions of a micron, for example 0.3 micron in per cubic feet. Okay, so a class 10 clean room means the number of dust particles of size more than 0.3 microns is no more than 10 per cubic feet. Okay, to give you some idea of what is involved in creating such a clean room, which is what is required for semiconductor processing. Okay, open air, the class is more than a million. It can be as bad as that. Okay, so a lot of cost and energy is involved in reducing this particle count to class 10. Then another stringent condition, okay, the water. You need water for processing materials. So the water should not have ions, it should be pure. So the water used in semiconductor processing is called deionized water. DI water. So how do you measure the cleanliness of water? You use the resistivity. Okay, resistivity of water. So the resistivity of tap water is about 20 kilo ohm centimeter, tap water. Whereas the resistivity of water that is used for semiconductor processing has to be as high as maybe 20 megohms. So you have to remove the ions from the water so that you get clean water. Then you have clean chemicals, ultra clean chemicals. So if you look at the bottles that are used, chemical bottles containing chemicals, if you have when you were doing experiments in chemistry, if you have taken care to see the labels on the bottles on the chemicals, there are several grades of chemicals, starting from the lowest grade like laboratory grade, then you have analytical grade, so then semiconductor grade, okay, And even in semiconductor grade now you have what is called the MOS grade, MOS, metal oxide semiconductor grade, because to make MOS transistors your cleanliness has to be even higher. So they have introduced what is called MOS grade chemicals. Okay. So gases also have to be similarly ultra pure. So these conditions are rather stringent. In fact, the amount of capital investment that you must do because of these reasons into a functioning semiconductor manufacturing unit is enormously high. Even a simple semiconductor unit making discrete devices, the investment would be something like 500 crore rupees. So it is said that if you want to compare different nations in terms of the wealth they have, all that you need to do is just count the number of semiconductor factories these countries have. Okay? So number of semiconductor factories is an index of the wealth of a country. So this is the reason why, even though the products are very useful and very high performance, okay, unless you have a large amount of capital invested into this, you cannot make these products. So you can call this as one of the limitations of the technology. Okay. Now in spite of the high capital investment, the cost of the product is becoming lower because the production volume is very high. You are able to generate new applications with products which are high performance, which are very light, and so your production volume is becoming very high, and that is how the initial capital investment, the cost that you are putting in, right, it gets divided, and that is why the computers and pocket calculators and so on are becoming so affordable. So one big unit trying to make large number of products, that is how this particular technology works. Okay. So it has its advantages and disadvantages. The disadvantage is only a very rich country or a rich man can set up such a unit, and then he or she may be able to control. That is a disadvantage of this. Okay. So there are many aspects of technology that one needs to understand. I have just focused here a few of them, okay, which are related to the semiconductor technology. Now another thing is the sophisticated equipment, which is also responsible for the high cost of the semiconductor unit. So most of the equipment, for example, that we use for this manufacture in India is imported. So you can see in this diagram also the clean air benches, okay, the environment which is maintaining higher level of cleanliness in the place that you are processing. The room itself is clean, okay, but the particular environment in which you are processing the silicon pieces and so on, subjecting it to various chemicals, is even more cleaner. Okay. So these, for example, here what you see, these are called the clean air benches. In fact, this person is processing in a clean air bench. The cleanliness is maintained of the air, a higher cleanliness is maintained by maintaining a slightly positive pressure in the region where the processing takes place. So the air is sucked in from outside through some filters, and then it is pumped into this region, and then the air flows out. So this way positive pressure is maintained, constantly air is coming out of that region. So that is how you can prevent dust particles and other things from entering into the region. Okay, that is how the clean air bench is made. Let us discuss some other things related to this technology. Products of semiconductor technology. Unlike in many other technologies, the use of the products becomes progressively easy with the advancement of technology. This is a very unique feature of semiconductor technology. To give you an idea, supposing you take automobile technology. In automobile technology, let's take the products which will reflect advancement in technology. Let's start with a cycle. Not really an automobile, but the simplest thing that gives you mobility. So start with a cycle, then go to a scooter, then go to a car, then you can go to maybe an aircraft, and then probably you can talk about a spacecraft. Okay. So you see advancement in technology, the person who is operating this vehicle needs higher and higher levels of skill. Almost everybody can ride a cycle, okay? Fewer can ride a scooter, and then for car again you need a much better training, and then you go to the aircraft, and then you go to the spacecraft. This is one example where as the technology advances you need higher and higher levels of skill to use the product. Whereas in the case of semiconductor technology, what you find is as the technology advances it becomes more and more user friendly, so even an illiterate person, right, can use this, can make use of the products. The level of skill required is very less. This is something very positive about this. Another unique feature of this technology is that the second point in the slide, that is performance of new products can be predicted using relatively simple models, and this is because you are using a single crystal material, right? Though single crystal material is difficult to make, but the performance of devices which are made in this material is easy to predict because you have regular arrangement of atoms, okay? So modeling is easy. That is why you have so many simulators and so on which are being used to predict new devices even before you make them. This is not something that is easy in other materials. For example, in glass and steel the performances cannot be predicted so easily because these are not single crystal materials, okay? Now let us come to the training required in semiconductor technology. The theory of semiconductors is abstract, and also if you see the technology in its totality, it is highly interdisciplinary. For this reason you need a strong training, okay, in mathematics as well as in sciences to really be effective in this technology. So a person who is doing working with steel or glass, the level of training required is much less than a person who is to be trained in semiconductor technology. So you will see that a semiconductor industry or lab, for example, appoints people ranging from mathematicians, chemists, physicists, material scientists, electrical engineers, right, chemical engineers. So they need people of all hues to really make the technology work. So that is why we have students undergoing a theory course before they take to the practicals. Those who are working with steel and glass can start playing with the material, and with a large number of trial and error they can come to some understanding of the material. But that is not the way one enters the semiconductor technology. One doesn't start playing with silicon, okay, and then you find you get interested, so let's understand this more and then let's take a course. That's not the way it works, okay. So you have a course on devices and so on and technology, and then you start practicing it. So let us look at the evolution of this technology. What I said just now, that a high level of training is required, this because in this technology the science came first and the empiricism has come later. Some of these features we will see when we see the sequence of events, which I am going to just talk about in a short while. Again, taking the example of other materials like glass and steel, people have been working with these materials for hundreds or maybe thousands of years. They didn't have an understanding of the atomic structure of or molecular structure of steel or the structure of the glass before they started working with these materials. But by doing lot of trial and error experiments, they have perfected the art of making better and better steel and glass and so on. The understanding of the structure has come only recently in last 200 years or something like that. Of course that must have also helped them to build better materials, there is no doubt, but a lot of progress has taken place even before the science of the materials was understood. But that is not true of semiconductors. In semiconductors first came the science, that is lot of experiments were done and they found that semiconductor materials have different set of properties than metals and insulators. Then they tried to understand the structure and so on, and after they understood the structure then they realized that maybe you can do a large number of things with this particular material, and that is how the this area has acquired importance. So this is what is meant by science first, empiricism next. Trial and error experiments come later after understanding the science. The only other example in this category is the nuclear science or nuclear technology. Even there the science came first and then the empiricism or the practice of this. The second important point is that in the growth of this technology, scientists, engineers and inventors, all these three types of people have contributed extensively. Often we use these terms interchangeably, scientists, engineers and inventors. Many times these are used interchangeably, but it is not true. If you try to look at the people who have been working and you understand what is science, what is engineering, what is invention, the type of people, their capabilities, their way of working is quite different. Okay? So a person who is a good engineer may not be a scientist. Similarly, an inventor need not be a good scientist, or there can be a scientist who is not an inventor. Okay? So these three types of people have contributed extensively to this technology. We will see a little bit on this science, engineering and invention because it has a relationship to this topic that we are discussing. Another important thing that you need to understand about evolution is that this technology, the interest in this technology was driven initially by the need to improve communications. How to improve communications, how to make communication faster, okay, more effective, that was the goal. So in the beginning it was found that this technology will help you to improve communications. That is how the interest developed. But after the technology developed, now the communication is being driven by all the developments that you have in this technology. It is the other way around now. The communication field is being driven by the solid state field. So let us understand the difference between science, engineering and invention. In science, the ultimate goal is publication of new knowledge, frequently mathematical. Okay, the ultimate goal of a scientist is to publish a book, a paper or something like that, okay, which establishes new links and patterns of understanding and integrates seemingly unrelated observations and phenomena into a grand pattern. That is the job of a scientist. So definitely a scientist is highly intellectually endowed, but the important thing is whatever he does, he or she does, need not result in a useful product. It is some sort of a publication which details this knowledge. As against this, since we are supposed to be engineers, at least IITs are supposed to produce engineers or inventors, okay, those who have a few characteristics. So what are those characteristics? Let us see. So engineering, the ultimate goal is the product. The requirements for engineering are knowledge of scientific principles and applied mathematics, hands-on experience, this is very important, hands-on experience. So if someone says that he or she is working in the area of semiconductor technology and is an engineer or a technologist, then it is not sufficient to just take a few courses and understand what are the fabrication steps for a semiconductor device and how a device works and so on. He or she must have hands-on experience, must have used the material, processed it and so on. Then ability to approximate, this is another important property an engineer must have. So engineer must be able to work with very simple formulae, derive simple formulae for design purposes. And then finally one aspect of engineering that is related to economics and so on. So unlike science, you cannot dealing engineering from economics that much, okay. So entrepreneurship, that is, you must have a person who sets up a unit that translates all this practical knowledge and so on into a useful product, okay. So entrepreneurship. So in fact the level of engineering in any country also depends on what is the extent of entrepreneurship in the society. How many people are trying to set up units which will make products. They might fail, but the question is how many trials are being made. So it is found that those countries which are advanced engineering, okay, their number of people who try to set up units, who try to be entrepreneurs is very, very high. If you compare, for example, United States and India. Okay, the United States, you will find the number of entrepreneurs is very large. Maybe 1 in 4 only succeed, okay, but the number who are trying is very high. So this is also an important requirement for engineering. Let us look at invention. What is invention? It is a useful new combination. Let us consider examples in the context of semiconductor technology. So I have given here 2 examples. One is called the planar process and the other is the pocket calculator. So planar process is a process invention and pocket calculator is a product invention. Let us discuss this point in little more detail. What is a planar process? In fact, the person who worked with this planar process, who used it for making ICs, has got a Nobel Prize recently. You know all of. Who is the person who got the prize? In fact, this is the only example where an engineer has been given a Nobel Prize for the invention, because the integrated circuit has revolutionized the entire electrical engineering, and in fact you can say the whole life. Okay, the number of systems, different kinds of systems that have been built, and the amount of new science that has been generated because in trying to understand integrated circuit is so large that the person was given a Nobel Prize. Okay, so that is why let us look at this planar process. What is this? You can make a diode as follows, which was the initial process that was used in olden days for making. When I say olden days, that means in the beginning of the evolution of semiconductor technology. That's maybe 50 years ago. So this is the structure of a p-n junction. Made by, this is the structure of a p-n junction made by what is called the MESA process. That is, the structure looks like a MESA pyramid. So here, how is this device made? Well, you have a wafer or a piece of silicon, n-type silicon, whole of which at the surface is converted into p-type. The size in those days could be 2-inch diameter. It is a circular wafer, a circular piece. The thickness of this is of the order of 200 microns. To give you a feel for this thickness, the human hair is about 50 microns diameter, right? Human hair is 50 microns diameter. So this is about 4 times the thickness of the human hair. This thickness all depends on this diameter, because you must be able to handle the silicon piece mechanically. So for 2-inch diameter wafer, it's about 200. Convert whole of the surface into p-type, but your individual diode is very, very small. So you have to separate this particular wafer into individual diodes. So how do you do that? Now that is where what you do is you etch out locally materials, something like this. And then you dice or break the wafer at these points. Now each of this device is what is shown here, separated. When you separate this particular wafer into devices, what will happen is this surface will be exposed to the atmosphere, this surface here, and impurities can get in there, and that will, which will spoil the characteristics of this diode. So what is done is you have what is called a passivation layer. This is passivation. So it is some material which you put here so that the surface, junction surface, is protected from environment. So this is the MESA process. Okay, what we want to talk about is the planar process. So after understanding the MESA process, now you will appreciate the innovation involved in the planar process. These particular diodes were quite leaky, that is, the leakage current was high. You see the diode characteristics. This is current versus voltage. So reverse characteristics, this represents the leakage current. That leakage current was high for these devices. Now let us look at the structure of a diode which is made by the planar process. So first I will draw the individual diode structure, and then we will discuss how this individual diode is separated from a complete wafer. This is the structure of a planar process, a device made by planar process. So here what is happening is this is a so-called passivation layer made of silicon dioxide. And what you find here is the junction is on a plane surface. That is why it is called a planar process. The junction is, the PN junction is exposed to the atmosphere, and that wherever it is exposed, that is on a plane surface. That is why it is called a planar process. All the devices are made on a single plane. Here, however, you can see that it is not a planar device, because the structure itself, as you can see, it is like a MESA. So advantage of this is now the PN junction is automatically passivated. It turns out that the silicon dioxide interface can be made of a very high quality, okay, and the leakage current of these devices is therefore much lower. That is not the only advantage of the planar process, or rather even the main advantage. The main advantage is now it makes it very easy for a person to integrate various devices on a single surface. That is the main property of the planar process. You can make different devices in a single plane. So I can have a diode like this, and then I can have a transistor, So this is an example where I am showing a diode and a transistor in the same silicon wafer. So this is a so-called emitter contact, this is a so-called base contact, and this is a so-called collector contact. They are all in the same plane. You look at this MESA process. Here, this is the top contact, and this is the bottom contact. Okay. Whereas for a PN diode, planar diode, both the contacts can be on the top. So this is P contact and this is N contact. That is what is happening here for a transistor also, that all the contacts, emitter, base and collector, are on the top, on the same plane. So you can integrate this very easily. I can run a metal line, supposing I want to connect, let us say this region to a diode for some reason. I can just run a metal line here and connect. So interconnection of various devices on a single plane, that is uniqueness of this, and it is this arrangement that enables you to build large number of millions of transistors or devices on a single silicon wafer, because you can go on shrinking the sizes and you can increase the density of the circuit. Incidentally, these two regions are called isolation regions, which should be p-type, so that the p-in junction along this area isolates this transistor from other devices and prevents unwanted interconnections between them. So a p-n diode, for example, made by planar process will have much lower leakage current than a p-n diode made by MESA process. Also MESA process will not enable you to integrate various devices. So here, how is this diode made? The sequence of steps is as follows. You take the same wafer, say n-type wafer, but the first step in the planar process is to grow the silicon dioxide layer, which is the so-called passivation layer. Then you etch windows, that is areas where you want the P region, you remove the silicon dioxide. And then in these regions you create P regions by diffusion, by a process called diffusion, that is introduce impurities through this particular window so as to create the P regions. Now automatically what happens is, since the impurities diffuse inside, they also diffuse sideways and the junction goes and sits under the passivation layer. Automatically it is under the passivation layer. Okay. So, and this, as I have said, the silicon dioxide interface can be made of a very high quality. It is possible to make very high quality interface using simple means, and therefore this is what enables you to get very low leakage current and very good passivation. Okay. The surface is protected against the environment. So now this was a process invention which made possible putting larger and larger number of devices in smaller and smaller area, the planar process. Now you have some such invention, it gives you a jump, okay, it opens up many possibilities. Now the next question arose that, okay, you have the capability of integrating large number of devices in a small area, but what do you do with this capability? What product do you make? Because this is also very important. What is a product that will be very useful out of this particular capability? So in fact, the one of the first products that were thought of was the pocket calculator. So someone said this technology we can use and we can make a small device which will calculate, okay, and everybody can have this device in his pocket, his or her pocket. So in fact when the suggestion was made, people laughed at it and they said this is not going to be very useful at all. Who wants to use a calculator, right? But nowadays we know that almost everybody needs a calculator. So the product invention of a pocket calculator is supposed to be a very important invention. It looks like a very simple idea, okay. That is how all inventions which are very wide applicability, all inventions which have wide applicability, their property is that they are very simple in their conception. So the pocket calculator is a product invention which showed how you can exploit this planar process capability, okay, and make a useful product. So having understood the science, engineering, invention, let us see how these three kinds of people have contributed to the growth of semiconductor technology. Here what I have done is I have listed a number of events, important events, in the chronological order. The events are listed for communications field, area of communications, because as we have said, the interest in this technology initially arose because of the need to improve communications, and then side by side the developments in solid state, the science of solid state, okay, semiconductor materials and so on. So one can trace it back to about 1820. The development that initiated the communications field was magnetism from electricity and vice versa, okay, Oersted and Faraday, the idea of electromagnetic induction and so on. So here you have the suffix indicated against the names of the persons associated with this event. S stands for a scientist, I stands for an inventor, and E stands for an engineer. So one of the purposes of this particular chronology is to show how a scientist develops an idea and then comes an inventor who exploits it and makes a useful product, right, that generates, that requires sometimes knowledge of some new observations. So again you have a scientist who comes in there and who explains some of these new observations. This results in more knowledge and new knowledge, which again there is an inventor coming in who exploits this new knowledge that is developed. So you have this sequence going on, okay, cycle, scientist, inventor, and so on. So here for example in communications you can see that after the development of after the understanding of ideas of magnetism from electricity, Morse was an inventor who came up and proposed the telegraph, how to use these ideas for communication. So this is communication with wires. Then you have a theory of electromagnetism being given by Maxwell. On the right hand side you can see the developments in solid state. Here the two strands are separate, there is no connection between them as of now, as in 1820. So you have a set of scientists studying the solid state materials. So thermoelectric property, right, so they were studying the thermoelectric property of various materials. They found some materials seem to be showing some unique features, okay, in this property. Then came the intrinsic property and photovoltaic effect by Faraday, studies by Faraday and Becquerel. Then photoconductivity. After studies of all these properties, there was an inventor who suggested that we can use these unique properties of materials. Till then it was not known, or the word semiconductor was not coined by 1870 or so on. Even in 1870s the word semiconductor was not coined. But the scientists had understood that there were some materials which behaved in a peculiar fashion, neither like metals nor like insulators. So Braun was an inventor who said that okay, you can put a metal to this contact to this material and it will have a rectifying property, instead of having a resistive property. That is, the current for one polarity of voltage is very different from the current for other polarity. And then he said that this kind of device we can use in communications for detection. Okay, so first device that was proposed by was an inventor, Braun, and thereafter again you have scientists studying the properties of semiconductors in the solid state field. Let us go further. Telephone was an invention by Bell, Alexander Graham Bell, for improving the communications. After that you had experimental proof of electromagnetic waves by Hertz, who was a scientist. Maxwell gave the theory for electromagnetism, but the presence of electromagnetic waves practically was demonstrated by Hertz. So moment this was demonstrated, came an inventor, that is Bose Marconi. There is still some confusion as to who is the original inventor of wireless communication. Latest information is that Bose was probably ahead of Marconi in this. Then you had vacuum tube diode and triode, again an inventor, okay, coming up and proposing this device for detection in wireless communication. Okay, radio waves. How do you detect the radio waves? You use this device for detection. On the right hand side here you see magnetoresistance being studied in solid state, and then the understanding of quantum mechanics by Max Planck and photoelectric effect by Einstein. Now it is in 1910 that the word semiconductor was coined. Okay, they found that this set of materials had so many unique properties that they wanted to give it a separate name, which is not an insulator, not a metal, okay, not a conductor. So the word semiconductor was coined in 1910. At around this time the communications field is still developing. You can see that positive feedback and sine wave oscillator. How do you generate the signals required for communication? Okay, this was the topic that was addressed by Armstrong. You proceed further. In the area of communications you have an engineer coming in here. After Armstrong also, as you can see, was an engineer and inventor. Okay. Similarly, Harold Black, who proposed a negative feedback, which was very useful in building good amplifiers, again for communication purposes. Then you had frequency modulation, Armstrong proposed. So you had a lot of development in the field of communications here. Now after 1920, because of the importance of radar in World War II, this is the important event which actually brought the communications and solid state fields together. There was certainly a lot of interest in the solid state area, because they found that using the vacuum tube which was being used for detection in communications, they could not go to very high frequencies. Okay? And that is where they found that the diode proposed by Braun, which was simply being considered as a rectifying device, was very useful as a detector. Instead of a vacuum tube diode, you use a solid state diode, right? It has much better, it is a very small size, it has a small capacitance, and therefore you can use it at high frequencies. So they started perfecting this device. Okay? Now this is actually the event where beyond this the solid state and communications, which were the areas which were separate, okay, they came together. And thereafter you can see here you have an inventor coming in this area of solid state, the semiconductor triode. How do you, if a bronze diode can replace a vacuum tube diode and give you much better performance, and people thought, why can't you replace the vacuum tube triode, the vacuum tube amplifier, by a solid state amplifier? So someone suggested how you can translate this idea of vacuum tubes into a solid state field. When we discuss the MOSFET, we will discuss about this particular invention of the semiconductor triode in little more detail, the field effect transistor. And thereafter the interest in the area of semiconductors grew really exponentially, and then came, you can see, a large number of models to explain the behavior of semiconductor devices, the important thing being, the first important model being the energy band model, then the theory of rectifying junctions and so on. And in around 19 1950, that is in exactly 1947, was the invention of the first solid state amplifier, that is the discovery, you can say, the BJT, bipolar junction transistor. So although the idea, the first transistor that was proposed is a field effect transistor, okay, the first device that was made is a bipolar junction transistor, because they were not able to make field effect transistor, and in trying to understand why field effect transistors were difficult to make, they discovered accidentally the bipolar transistor. So and then thereafter you have the planar process being used for integrated circuit by Noyce and Kilby. So in fact Kilby got the Nobel Prize for his invention of integrated circuit. And thereafter now we have the solid state area progressing and driving the communications. So you had a series of devices being proposed, MESFET proposed by Mead, then you had medium scale integration, the integration of devices into a IC started, filters, then you had large scale integration being used for making a random access memory and analog to digital converters, microprocessors and so on. Then in 1980s you had the HEMT, high electron mobility transistor, and then in integrated circuits you had VLSI, that is 64 kilobit random access memory. In 1990s you had 3-dimensional integration, that is you integrate not only on a plane but also in the vertical dimension. Now most recently we have had nanoelectronics coming up, wherein we make devices out of either nanocrystalline materials or we make devices which are of nano dimensions but made in crystalline materials. Now next, after having seen what is the way the semiconductor technology has evolved and how scientists, engineers and inventors have contributed to this evolution, let us briefly review what is the status in India of this technology. Broadly we could divide the technology into 3 levels: the software level, the hardware level which involves architecture and assembly, and finally the devices or components level which is heavily dependent on materials. The capability index for these technologies is indicated here. We are doing very well in software, so A, that is excellent or very good, we are exporting software. Hardware level we are good, we can make supercomputers and we are sending satellites into the space. So this level involves integrating components and making systems. However, at the devices or components level we need improvement. That is, presently the level is not satisfactory, U stands for unsatisfactory, and we are improving but we need to improve more. The reason why we are weak at the devices or components level is because we are weak in the area of materials oriented technology. So we import the technology for making sewing needles, which is based on the steel, processing of steel material. So it is not surprising that we import technologies for making semiconductor devices. Semiconductor and steel both are materials. Now the chain is only as strong as the weakest link. So the level of engineering or technology in India can become excellent only if all the 3 levels we are strong and the chain is strong. Now let us see, as a part of the status in India, what are the various industries, research laboratories and academic institutes which are participating in development of technology. So in industries we have Bharat Electronics Limited, Bangalore, Continental Devices India Limited, CDIL, New Delhi, then we have Semiconductor Complex, Chandigarh, then we have Indian Telephone Industries, that is ITI, Bangalore. Some of the research laboratories are the Solid State Physics Laboratory in New Delhi, the Central Electronic Engineering Research Institute, CERI, in Pilani, Rajasthan. Then there are academic institutes which are participating in the development, which have small laboratories but which have strong teaching programs in this area. These are the Indian Institutes of Technology and the Indian Institute of Science, Bangalore. One of the purposes of developing the video lectures is to have more colleges in the country involved in teaching of this technology, which is advancing rapidly. Now in the end of this lecture, I would like to tell you what is the way the remaining lectures will be conducted. So for the remaining lectures, we will have 20 minutes of lecturing followed by about 8 minutes of discussion, and then we again have 20 minutes of lecturing followed by about 8 minutes of discussion. This is an approximate idea of the division of the time of 56 minutes into lectures and discussion, which involves question answers. Then problems and solutions are provided in a separate CD. Some problems will be solved in the class, but some will be given to you, and you will have to solve them yourself. These are provided on a separate CD. Then we also have a separate CD for discussion of select problems and their solutions. And finally, what are the reference materials? Where apart from listening to this video lectures, you could refer to textbooks which are available. There are many textbooks such as textbooks by MS Tyagi of IIT Kanpur on Introduction to Semiconductor Materials and Devices. In addition to, and then Ben Streetman, his book on semiconductor electronic devices. Now apart from this, I would also urge you to use the internet for understanding various concepts, and I will demonstrate to you in the remaining lectures how internet can be used.